Hello everyone. So welcome to the first Kalanov seminar of this semester. So today we are very happy to have Corey Jones from North Carolina State University. And he has done a lot of interesting works on operator algebra, topological order, mathematical physics, category theory, and so on. So today he will talk about his theory on symmetric quantum cellular automata. So let's welcome.
Okay, thanks for the introduction. I'll start off with a word of warning. I'm a mathematician, so if this talk seems super weird, like, what is this guy talking about? It's probably because I'm a mathematician. So please feel free to derail what I'm saying and take it any direction that you want to with questions. Okay, good. So first I want to start by telling you about the algebraic approach to spin chains. So usually, right, we start with a local Hilbert space. It's just C to the D, right? Qubits or whatever you want to call them. Then for each interval, I subset of Z, we have this algebra, which I'll call A sub I, which is just the tensor product of D by D matrices with the tensor factors indexed by the points in the interval. Right, so it's just a discrete thing. These are the operators, right? The observables or whatever the operators, unitaries that are localized in this interval. And if we have a containment of intervals, we have a natural inclusion of these algebras, which just effectively takes an operator that's localized in some interval and it sends it to, you tensor with ones on the outside. Okay, so if J has a bunch of extra slots that I didn't have, you just stick ones in there. And this is a homomorphism of, these are actually finite dimensional C-star algebras, but this is a homomorphism of these kind of associative algebraic structures. Okay, and what you can do is you can take the thermodynamic limit by taking the union, and I'll put this in quotation marks. The technical term would be a co-limit in the category, but you take the union over all intervals of these AIs. And you have an option here to complete it if you want to in some norm. There's a unique norm on this that makes this into a C-star algebra, and you get what's called the quasi-local C-star algebra. So you can still do all the physics in the thermodynamic limit that you want to do, right? For those of you who have thought about, talking about states in the thermodynamic limit, the infinite Schindler product Hilbert space is this gross technical object that has a lot of issues with it. But you can do all the physics you want to do in the Heisenberg picture using this algebra, which is very clean. So mathematicians tend to prefer, when they're talking about thermodynamic limits of spin systems, to do everything in terms of this algebra. So for example, a state in the thermodynamic limit will just be a positive normalized linear functional in this algebra, right? So that's easy. Time evolution will be some continuous one-parameter automorphism group. A Hamiltonian will be a derivation on this algebra and all this sort of stuff. So this is useful for taking the Heisenberg picture. Okay, and the thing that I actually want to talk about today are local Hamiltonians. So what is a local Hamiltonian? It's basically a big sum of these HIs over all intervals, where the I is interval. And the point is that this HI should be an element of the A sub I, so it's localized in this little interval. And the key point is that I should have that for sufficiently large intervals, these HIs are going to be zero. So the only interaction terms, you should think of these Hamiltonians, these terms, these HIs as interaction terms, the only interaction terms are localized. There's some sufficiently large R, so such that for any interval whose length is greater than R, these HIs are zero. So that's what I mean by localized. So such that there exists an R with HI equals zero for length of I bigger than R. Okay. And so when you're studying Hamiltonians on spin systems, there's a bunch of different notions of equivalence. So for example, if you're studying gapped Hamiltonians, you might consider adiabatic equivalence or something like this. But one natural notion is the following. So if I have two spin systems so this is one spin system, quasi-local algebra with local Hamiltonian. Here's another spin system with maybe a different quasi-local algebra and a different Hamiltonian. Then we can define these to be equivalent if there exists an isomorphism of algebras. So it's taking the one quasi-local algebra to the other, such that there's an R bigger than 0 with alpha of a sub I contained in b sub I plus R, where if I have some interval I here, then I plus R is just the thing that I get from extending it R on either side. So here's my I plus R. Okay. So this isomorphism of this abstract isomorphism of algebras is locality preserving, but not in a strict sense. Just in this sense that there's this globally kind of uniform R that will change the support of an operator at most R. It'll at most expand it or shrink it by R.
There's no condition on the Hamiltonian.
So just this locality condition. So no, good. So this thing has to map one Hamiltonian to the other. Yeah. So I was just trying to explain this condition here. So this is what's called a bounded spread isomorphism. So such that, yeah, right. So I was talking about Hamiltonians. So I need that if I take alpha of the HIs and I sum over all I, and I look at how it acts as a commutator with anything in B, this should be equal to the sum over I of the KIs. So I'm not requiring that the individual terms map to the individual terms, but kind of the global Hamiltonian, which you can kind of see in this Heisenberg picture, instead of thinking of these as acting on a specific Hilbert space, you see the action of the Hamiltonian by taking commutator with local or quasi-local elements. I want this to, sum over. I want them to act kind of on the observables, the local observables in the same way after taking summation. So that's what I mean by one notion of equivalence of Hamiltonian. One reason that this is natural is this bounded spread condition said it means if I take any old local Hamiltonian and just apply a bounded spread isomorphism to it, I'll still get a local Hamiltonian. And if you use other kinds of isomorphisms here, that's no longer true, right? If I plugged in some local Hamiltonian into something that didn't satisfy this, it may not be the case that the thing I get is expressible in this way in terms that have kind of a bounded support on their interactions. Okay, so this is one natural notion of equivalence. And so it motivates, you can ask the question, well, what about, can we just kind of classify these sort of things? And then once we know what these sort of things are, then we can kind of plug in our Hamiltonians and think about equivalences. And indeed we can. So it turns out that you might as well be looking, A and B might as well be the same thing. So we'll just look at bounded spread isos. Bounded spread isos from alpha from A to A, and these are exactly what are called quantum cellular automata. Are just bounded spread isos from A to A. So this is another word. Yes.
So the fact that you've restricted A to A, like does this like exclude stuff like tensoring in trivial degrees of freedom?
Yes, this does. So there are additional equivalence relations. So I'm not saying that this is like the best or the only equivalence relation, but this is an interesting equivalence relation that often when people are doing classification will add in other things like adding ancilla qubits or whatever on every site. But yeah, this does restrict from that. That's not kind of an allowable move under this notion of equivalence. Yeah. Yeah, so mathematicians often will trade generality for precision. Like if we have a really concrete definition that we can actually prove a theorem about, we'll trade that for it being general to cover all the cases. Okay, so if you take bounded spread isos from alpha from A to A, these are called quantum cellular automata, and these are always composed of finite depth circuits. And generalized translations. And this is a result due to Gross, Nesmet, Vault and Werner, I believe, from around the 2009 period, 2010, I'm not exactly sure the date, so apologize to get that
This
wrong.
doesn't depend on the dimension of it?
No, this is all one dimension.
Oh, I see.
So yeah, so I'm only working in one dimension. This is of course something very interesting to do in all dimensions, but this theorem definitely only applies in one dimension. Okay, and the way that they do this is they define a numerical index, and they show that the kernel of the numerical index is exactly the finite depth circuits, and all the other indices are saturated by generalized translation. And what do I mean by generalized translation? So what a generalized translation is at each point, imagine I have a factorization of the dimension into p times q, so I can factor my matrix algebra into a tensor product MP tensor MQ at each site, and then I can shift all the p's and leave the q's fixed. Or I could shift the q's the other way and leave the p's fixed, or I could do both. So it's kind of like you do a factorization at each site and then you shift on some of the factors and shift on the other factors. And then so that's what I mean by generalized translation. Okay, so we know what's going on there. And so essentially this isn't very interesting, this kind of equivalence relation that I wrote down here, in the sense that bounded spread isomorphisms are kind of boring-ish. We understand what they are, at least in 1D. Okay, certainly not the case in higher dimensions.
So could you maybe say, I don't know if this is exactly well posed, what happens to this theorem and results if you include ancillas?
This theorem and results?
Yeah.
Yes, so the theorem is still true. It's just if you want to actually classify the equivalence classes of the generalized translations, you extend what's possible. So if I fix my dimension D and look at this, the actual, you can actually write this group down. The QCA is there's a short exact sequence between finite depth circuits, QCA, and then a specific subgroup of the multiplicative rationals. If you stabilize, you expand it to all multiplicative rationals, if you kind of infinitely stabilize. So you just kind of like the range of the index increases. So the group changes, but this result is the same. It's just what generalized translations are. You now have a lot more possibilities of generalized translation. So it's morally the same.
But you basically allow any factorization of.
Yes, yeah, because I can stabilize it. Exactly. Right. Okay, but so what I wanted to talk about today was not really this story. What I wanted to talk about are actually dualities. And I know dualities is maybe an overloaded word in physics. We have a lot of those in math too, where like the same word means like 100 different things in different contexts. According to Wikipedia, duality is like an equivalence of theories, right? Just some notion of equivalence. So from that super general definition, I guess these would technically be dualities. But you know, talking to my physicist friends, dualities are more about vibes. Like, does this have the vibe of a duality? Does this feel like a duality? And there's different vibes, right? There's like ADS CFT type vibe, where your whole geometry is changing. There's like electromagnetic, electromagnetic duality type vibe, the original duality vibe. But the kind of vibe that I'm talking about are the Kramer-Twanier duality vibes. Sorry, Kramer, it's 1M2. I think it's 1M. Okay, so those are the kind of dualities I do. And the idea here is, instead of talking about an isomorphism between these spin systems, that these quasi-local algebras that take one Hamiltonian to the other, the idea is to pass to a sub-algebra. So instead of using the whole set of quasi-local operators and asking for an isomorphism between them, you pass to some sub-algebra that contains the terms of the Hamiltonian. So pass to sub-algebras, A circ, subset of A, B circ, subset of B, such that, you know, the HI are contained in A circ, and the KI are contained in B circ. And then you ask for the same thing to be true, but just with the bounded spread isomorphism between A0 and B0. So then a duality is a bounded spread iso alpha from A circ to B circ with something like sum of alpha of hi. Same thing. Okay, and so that's what we mean by duality. Yes.
Yeah, I know you said you work in just one dimension, but could like an edge theory be an example of this?
Yes, absolutely. Yeah, our main examples will be realized as edge theories for sure. Okay. And okay, this framework makes sense in all dimensions.
Yeah.
Okay, I'm just gonna tell you about examples and theorems in one dimension, but this general framework, yeah, makes sense in any dimension. Okay, and so the canonical example is indeed it's Kramer-Wanier. It's an S here, Kramer-Wanier. So what's the Hamiltonian? Well, it's just the standard Ising Hamiltonian. Sigma I Z, sigma I +1Z, H, sigma X. So what subalgebra are we going to use? Well, the idea that the smallest one that you could use is just take the subalgebra generated by these terms separately. Okay, and that's called the bond algebra. Sometimes people call it that. So define A0 to be the algebra generated by the set of sigma I Z, sigma I +1, Z, comma, and the sigma I x's. So this is a subalgebra of A. It's not the whole thing. And another way you could think about this is if you think about the diagonal Z2 action, just from spin flip. So diagonal sigma I x's, the product of all of them acting, these are the local symmetric operators. So you can also think of these as just this as a symmetric subalgebra. And then the duality that we have in mind just sends, let's see, can you all see this? Probably not because of that. Let's see. Board calculus. I love these things, but I have not figured out the algorithm for what's optimal. So what should I write on the backboard? But then you can't see the one I just wrote on. Just do the front two. Okay.
Blackboard lights, someone, does anyone know where the switch is for the blackboard lights?
Okay, so the duality sends, let's see, I believe it sends sigma I, Z, sigma I, so it sends this generator to sigma I x, and it sends this generator, sigma I x, to sigma I -1, Z, sigma. Okay, and so you can check that this actually gives you a bounded spread isomorphism in this algebra to itself. That takes this Hamiltonian to itself, and it basically switches the terms, right, under this thing. So it flips the H and the J.
Can I ask a question?
Yes.
So how do you choose the subalgebra?
Yes.
Is it kind of depends on what kind of thing you're going to prove?
Yeah, that's the art. So you don't necessarily, there's not a canonical choice. That's kind of, when you discover a duality, you found a cool subalgebra that you could use. The criteria is that it has to contain the terms of your Hamiltonian, but even the terms of your Hamiltonian is not really a well-defined thing because I could express
the Hamiltonian is just the sum of that, right?
Exactly.
So it's one
No,
way
so
to
it's not even really a well-defined thing in the beginning. But if you have it expressed as terms, then this one thing you could do, which is kind of the smallest thing you could do if you want those particular terms to live in there, is to take the algebra generated by the terms. And indeed, that works in this case. So, but again, yeah, you have to already know that I should care about those as my terms in this decomposition. Yeah.
Is it okay that this math is non-local for a single sigma z?
What's that?
Is it okay that this math is non-local for a single?
So it's actually a bounded spread isomorphism. So it's local in this sense. It'll take the operators in A0 that are localized in an interval to operators that are localized in an interval one step larger. One of the important features about duality that we witness here is that this bounded spread isomorphism does not extend to a bounded spread isomorphism on A. So a duality, we said, is a bounded spread isomorphism, but the interesting ones are the ones that have the kind of Kramers-Wanier vibe, are the ones that don't actually extend to a bounded spread isomorphism on the whole theory. You can only see them when you restrict to these subalgebras, and that's the key point. So that's an important thing to notice, is it doesn't extend to a bounded spread iso, alpha tilde from A to A. At least it doesn't extend in a bounded spread way. Okay, so that's kind of what gives it the right kind of feeling. It makes it kind of interesting, is you only see it when you have this subalgebra. You don't see this. In this case, it's the same Hamiltonian, so this is a self-duality. Right, and of course, you know, Crummers 1 here was originally formulated in classical statistical mechanics, and you can use it to compute the critical value exactly of the 2D IC model, right? That was one of the really interesting things about this, is because it gives you a symmetry of the equilibrium of the partition function and things like that. So yeah. So anyway, okay, so that's the idea. And so what we're gonna do is talk about kind of a general framework for looking at these sort of things. When there's fusion categorical symmetry. So let's let, I'll say it this way, I'll write it as this for now. Be some kind of global on-site maybe symmetry. I'll put these in quotation marks. Symmetry. So what do I mean by this? So of course, if you just like groups, you can think of groups. And I have in mind for the purposes of this talk finite groups, but of course any kind of group will work. If you're a little more ambitious, you could think Hopf algebras. And if you're really crazy, you could think weak Hopf algebras. These are essentially the same thing as what people call MPO symmetries, matrix product operators, or categorical symmetries. Okay, in all these cases, what do they have in common? There's something that's acting on my spin chain, and the key thing that makes this work is that there's a notion of symmetric operators, of local symmetric operators. Whatever kind of version of symmetry you want, as long as there's some version of symmetric local operators, then that kind of specifies a subalgebra that's suitable for doing dualities. Okay, and in general, you get this symmetric subalgebra, A sub G, and it's not always going to be a subalgebra of the spin of the original quasi-local algebra in an honest way. Sometimes you have to actually look at, it's only going to be a subalgebra of a full corner, where this is a projection in the double dual von Neumann algebra, blah, 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 don't worry about it. But if you know what I'm talking about, this is like, you know, in Levin-Wen type models, sometimes you can talk about the edge restricted sector, which is a non-topological sector, but you know, but sometimes it's useful to restrict to that. That's the kind of thing that's going on here when I say this. But if you're talking about group or Hopf algebra symmetries, you can just ignore this P. So if you don't know what I'm talking about, just think of it, ignore the P. These are the symmetric operators. So in all of these cases that I was talking about here, you can actually identify this algebra and kind of this local structure in an abstract way as what's called a fusion spin chain. So in all these cases, AG is abstractly fusion spin chain. So can I get a show of hands who knows what a fusion category is, roughly? Okay, that's sufficient for that. I'm just going to keep rolling with that. I thought that might be the case with this audience. So what is a fusion spin chain? So I'll give you the abstract definition. It depends on two things. C and X. C is going to be a fusion category, and X is just going to be some object in that fusion category. And this object doesn't have to be a simple object. It can just be any old object. It can be a direct sum of simples. What time does the seminar go to, by the way?
2:30.
2:30. Okay, great. So where C is fusion, and in fact, it can even be more general. It can be multi-fusion, but we'll stick to fusion category. And X is an object. Okay, and what I do to build one of these things is I mimic the construction that we did at the beginning, where I define an algebra, finite dimensional algebra for every interval, and then I will take inclusions of them, and then I'll take some big kind of limit, and that will be my big kind of analog of quasi-local algebra. And it'll have all these local algebras sitting around inside of it that by construction, and so it makes sense to talk about things like bounded spread isomorphism and stuff like that.
What's the non-abstract definition?
The non-abstract definition of this would be like symmetric operators under some concrete symmetry. So like over here, if I had some symmetry, like if I have a group acting, I can just say, okay, I'm gonna take the quasi-local operators that are invariant under that group symmetry, and that's a thing. But I can go off and abstractly just use, so in that case, I would use the fusion category rep G, and I would think about the representation of G acting on the local Hilbert space as an object in that fusion category, and then I could build an abstract one, and it would turn out to be equivalent to that one. Okay, and in fact, in all these scenarios, it's something exactly like that's what's going on.
I wonder if you can say some of this in terms of the language of gauging. So, you know, in the Kramer-Zwania case, we would have said that to extend the whole algebra, the full duality statement is the Ising is dual to a Z2 gauged Ising.
Right.
And then it's definitely non-local, but it extends to the whole algebra and gives us kind of a physical picture of what the true duality statement is at that level.
Indeed, yeah. So it may be that there's a general story there. Yeah, I'm not sure what exactly that looks like, but yeah, for sure. Okay, so let me give you this concrete thing. So for each interval I, I'm going to define my algebra A, C, X sub I to just be endomorphisms in the fusion category. This object. So I take, you know, these are just pictures that I draw like this, where I have these strings that go by my objects X, and I just take all the morphisms I can draw in my fusion category from X to the n to X to the n. Okay, so if you want to, right, you could represent these in like a tree basis or a fusion basis, where you represent these operators kind of, I guess, paths in some fusion graph, and all that sort of stuff. And the idea is that if I is inside J, you have a natural inclusion, again, between these things. By just adding strings to either side in my graphical calculus. So in this fusion basis, this can be more complicated because when I add strings, I have to go in here, resolve the parallel strings with alpha alpha star, and then apply my 6J symbol to like put it back in this form. So even though in pictures these look quite simple, the actual, if you want to write down in terms of some fusion basis what's going on, it can be pretty complicated formulas in terms of the 6J symbols. But nevertheless, you have these inclusions sitting inside each other, and you can take the big limit, and you get an algebra, which we call a fusion spin chain. Like it's really more like the algebra and all of these local subalgebras together is what we're calling it. Okay. So I have A, C, X. It's just like before, it's going to be the union of these A, C, X sub i's. And optional, depending on what you're trying to do, you can complete it in norm and you get a quasi-local algebra. And so this algebra is what we mean by fusion spin chain. It's just the kinematical content or the observable content of the thermodynamic limit of a symmetric thing. Like that's how we should be thinking. So now that we've sufficiently abstractified it so that I have a chance of understanding what's going on, now I can ask you a question. Can we try to understand bounded spread isomorphisms between these? So if I pick a fusion category in an object and you pick a fusion category in an object, can I tell you, just in terms of the choice of fusion category in the object, what all the bounded spread isomorphisms are going to be? And maybe if I have them realized inside a concrete spin chain, can I tell you when those things actually extend? Because remember, the dualities were most interesting when they didn't extend to bounded spread isomorphisms between the bigger concrete spin system. So questions, can we classify these? And I have in mind some kind of classification that's analogous to the GMVW classification, right? Where they said everything is one of these generalized translations and a finite depth circuit. Like, can we do something like that? Can we classify these? And preferably, can we classify them in terms of kind of categorical data about that fusion category and maybe something about this object? And second question is, can we determine when these are spatially implemented, or maybe I'll call them unitarily implementable or something like that. Can we determine when these have spatial implementations? Implementations. So what I mean here is when this abstract fusion spin chain is kind of realized as subalgebras of some concrete one, can you tell me when this bounded spread isomorphism between the subalgebras extends to a bounded spread isomorphism between the real quasi-local algebras, the actual infinite tensor product? And in the case of a fully general fusion category symmetry, it turns out that using just pure category theory, you can't get rid of these projections there. So when I say spatial implementation, I'm kind of lying and I'm including those projections in there. But if you just care about group symmetries or Hopf algebra symmetries, then you can ignore that. Okay, and then it really is what I'm saying. Okay, any questions?
Wait, sorry, I didn't understand this last point. By spatial implementation, you mean, can I realize it as some, I don't know, projection of some, tensor product thing? Is that?
No, no. So a spatial realization of the spin system is realizing this inside here. A spatial implementation of a bounded spread isomorphism or of the duality is an extension, like so in particular, so let me say it like here. So suppose I have a bounded spread isomorphism between something like this, where this is some other H acting on some other spin system. And this is sitting inside, say, A, and this is sitting inside, say, B. Can I extend it to a bounded spread isomorphism? Because the whole point of Kramer's Wannian is that you couldn't do that, right? You could define this bounded spread isomorphism on this special subalgebra, symmetric subalgebra, but it didn't extend to a bounded spread isomorphism. So some people call this sort of game non-invertible symmetries because you can always extend it, just not to a bounded spread isomorphism. You can extend it to something, maybe a quantum channel or whatever. You can always extend it, but it won't be an isomorphism, and so people say, oh, it's non-invertible. Or sometimes you can extend it to an isomorphism, especially in the regular spin system case, but it won't be locality preserving, or it won't be bounded spread. It'll map local operators and non-local operators. So in other places, people are talking about the same thing, use slightly different language. But what I mean here is the concrete definition. Can I extend this bounded spread isomorphism to one here? To a bounded spread isomorphism. And so that's what I mean by spatial implementation. And of course I'm lying because I really mean this. Something like that. Yes.
So when you're doing that extension, you're still not extending it to the full.
Well, it depends. So it depends on the embedding. So in many cases, this is really, yeah, you're right. So in many cases, like for example, if a group is acting on site, then you are extending to the whole one when you answer this question. But when it's like a fusion, like an MPO symmetry, and it's like an honest MPO symmetry, then yeah, you're still not extending it to the whole one, and you actually generally can't do that in any kind of, you can't answer that question, at least from the point of view of category theory.
You could like come up with some like specific like algorithms or how you map like different operate, like what operator you put in between P and the P's, right?
Yes, yeah.
So they're just not unique.
Yeah, that's right. Okay. So I'm going to tell you a bit about some stuff. So I should mention, one of the things that I'm not actually going to write down on the board in the interest of time is the first thing that I tried to do when thinking about this question was to write down an analog of the GMVW index that works for fusion spin chains. Because a lot of this stuff, so the key thing that's going wrong with fusion spin chains and why a lot of your intuition about regular spin chains doesn't work is there's this thing which I call maybe tongue-in-cheek algebraic entanglement, which is the following. Usually, if I have, an interval, a disjoint union of two intervals, right, where I intersect J is empty, then if I take the algebra of operators localized in AI union J, it's the tensor product, right, of these two things. So it kind of splits algebraically as a tensor product. It's like algebraically separable. But in fusion spin chains, this is not the case. So fusion spin chain. Okay, and so a lot of the things that you try to do, like when you look at the GMVW index and how it works, you take support algebra, it just doesn't make sense anymore because you don't have this tensor product decomposition. So the idea is, how do you utilize that? How can you kind of measure that algebraic entanglement and use it to your advantage? Because maybe the way to classify these bounded spread isomorphisms between these fusion spin chains is to think about how they interact with structures that are reflecting this algebraic entanglement. So the first thing that you can try to do, that I did with a graduate student, Juhui Lim, is we wrote down a generalization of the GMVW index using what's called the Jones index for subfactors. And we showed that it actually, you get this nice generalization, it actually works as an invariant, and it actually does classify QCA up to finite depth circuits on in one example, the Fibonacci spin chain. But I realized that it can't possibly give you a general classification. So the whole thing that I'm going to talk about today is the other side, like why that can't be the whole story and why it's probably just a little piece of the story. And I'm going to talk about kind of the other piece of the story that I've kind of been thinking about so far. That kind of is directly trying to measure this algebraic entanglement with some other kind of mathematical object or structure. Okay. So this is the theorem. So associated to any abstract spin chain. So really, it doesn't even have to be a spin chain, abstract spin system. Works in any dimension. And what do I mean by an abstract spin system? It's just some big algebra that has all these subalgebras, like these A sub i's, these localized subalgebras that kind of commute with each other when they're localized in disjoint regions. So there's some abstract axioms that go into defining what I mean by an abstract spin system, but you should think it's something like one of these fusion spin chains that has like a big algebra with these local subalgebras. So associated to one of these is a braided C-star tensor category. Called the category of DHR bimodules. I'll call my abstract spin system A circ. I'll use the circ so that we know, I'll reserve just A for like a real concrete spin system and A circ for one of these abstract things. So it's a braided C-star tensor category DHR of A0. Okay, and any bounded spread iso alpha between two of these abstract spin systems gives you a braided equivalence between these braided C-star tensor categories. I'll call it DHR of alpha. And it maps between these two categories. So from DHR of A circ to DHR of B circ. So let me go ahead and pull that up so y'all can see it. There you go. Yeah. Okay. So the idea is that associated to one of these abstract spin systems, there's this DHR category that, the reason it's called DHR, it stands for Doppler, Hagen, Roberts, who did something very similar in the context of algebraic quantum field theory in the 70s. So, they were looking at, real quantum field theories on Minkowski spacetime, and they wrote down this kind of abstract theory of superselection sectors. And the idea was to modify that construction to work for one of these abstract spin systems, and so that's what this thing is here. It gives you a braided C-star tensor category. And the idea is that it's meant to exactly characterize this algebraic entanglement. It's meant to not just say, okay, there is algebraic entanglement, but give you a qualitative but concrete description of how that algebraic entanglement behaves. So how is this failure behaving? And the idea is that this braided tensor category is supposed to measure that for you, okay? And then the theorem is that, okay, if you had a bounded spread isomorphism between two of these things, then it implements a braided autoequivalence between these braided categories associated to this. So in particular, if you have a spin chain and you have a QCA, so a bounded spread isomorphism from this to itself, and you know what this DHR braided category is, it's one of your old friends, maybe it's like, the Drinfeld double of XC2 or something like that, then any one of these QCAs will give you an autoequivalence of that category, and so you can treat it as an invariant. kind of like a topological index. It's an index in the flavor of GMVW, but instead of being valued in numbers or numerical index, it's valued in braided autoequivalences of a category. Okay, that's the idea that this was supposed to do for you. And the companion theorem, which makes this useful, is that for fusion spin chains, guess what that braided category is going to be? So in math, you do the way you play this guessing game is you say, okay, here's a fusion category. What could I possibly have? How could I have a braided category associated to that? Drinfeld center, indeed. So that is the theorem. So the theorem. So if I take the DHR category of this fusion spin chain, this is equivalent to the Drinfeld center of C under some assumptions. So not assumptions, under some hypotheses on X. So X has to be self-dual. That assumption is probably not necessary. I just was feeling lazy. And instead of reproving something, I wanted to use someone else's theorem, and then using self-dual made that easy. The extra condition, which you can't get rid of, is what's called strongly tensor generating. And that means that there's some fixed n, so that every simple object in the fusion category occurs as a sum n of x to the n. So it's stronger than just saying it's generating, which means, for every object, there's some n, such that that object is contained in x to the n. There has to be one n where all the simple objects are occurring at once. Okay, and so, for example, if you're looking in the category of rep G of a finite group, then the left regular representation is such a thing that satisfies this hypothesis. Yes?
Are there like famous examples that don't satisfy this?
No, because yes and no. So what happens when you don't satisfy this hypothesis is that you're really working with a different fusion spin chain. And so this is actually what happens in Kramer's Wanier duality, is that if you use the Ising fusion category, which is like this Tambar-Yagami of Vexy2, and you use that row is not strongly tensor generating, because when I square it, I land in Vexy2. Yeah. But now you can use that as a generator for Vexy2. And so if you tried to build that fusion spin chain with Ising category, you would actually be working with the Vexy2 fusion spin chain. So yes, there are examples, but they reduce to other things. So it's kind of without loss of generality, if that makes sense. Yeah. Yes.
If I go back to a not abstract spin chain, what is
Yeah.
the DHR?
It's trivial.
True.
Yeah, because a non-abstract spin chain is an abstract spin chain with a trivial fusion category. If you put the category, what's a trivial fusion category, finite dimensional Hilbert spaces, pick your favorite object there, I don't know, C to the D, then build this, and okay, it's the abstract fusion spin chain is a concrete fusion spin chain. So this really generalizes concrete spin chains. It's not really like a orthogonal move from.
So there's no, like, the translations, the generalized translations are not sort of.
Yeah, so this tells you no information in the concrete. So like the index, the GMVW index is giving you kind of orthogonal information to this. This is information that is only relevant in this algebraic entanglement setting. There's only new interesting information. This is kind of measuring the algebraic entanglement. But the hope is that I mentioned that GMVW index, that the generalization that I mentioned that I had, is like combining these two might give you enough information to get a complete classification, but we don't know how to do that. But that is a kind of loose conjecture. That somehow the invariants that we have for QCAs, at least to classify them up to finite depth circuits, are kind of enough. But yeah, that's just a conjecture. But anyway, okay, so let me explain to you what's going on in the, let's just see what's going on in the Kramer's Wanier case, our one kind of the one true example. Okay, so example is Kramer's Wanier. So here, take your fusion category C to be rep of Z2. And take your object X to be the left regular representation. So it's just Z2 acting by spin flip. And think of that as an object in this fusion category. Then the fusion spin chain is exactly the, so if I take the fusion spin chain with rep Z2, and I take this regular representation, This is exactly equal to that algebra, or it's isomorphic to the algebra generated by the Z's and the, the bond algebra that I wrote down earlier. Okay, and so according to this theorem, that means that the DHR category of this is going to be the Drinfeld center of XZ2, so the Tor code modular category. So I'll just call this A cert for now. Drinfeld center of, and I guess everything's unitary, so Hilb Z2. Okay, so according to that theorem and this theorem, Kramer's 1A duality, which is a bounded spread isomorphism of this, should give me a braided autoequivalence of the Drinfeld center of Hilb Z2. And it gives you the EM swap. Well, I didn't tell you how to define this braided category. Maybe I should have said something about that, but if you're interested, ask me later. I'll just keep going for now. But the basic idea, maybe I'll give you an idea. I didn't tell you how to define this. But what you do is you look at this algebra and you define a tensor category of bimodules over this algebra that satisfy some nice localization properties. Okay, so if you're familiar with the DHR theory from algebraic quantum field theory, what you do there is you look at endomorphisms that are localized in little light cones, but they're isomorphic to ones that can be localized in any little light cone. And the idea is to come up with a version of that, but uses bimodules, because endomorphisms aren't sufficiently interesting to capture what's going on here, because our algebras, which are von Neumann algebras, are not type 3 von Neumann algebras. So you can't use the endomorphism picture like you can in DHR, but nevertheless, you could come up with like a category of bimodules. Philosophically speaking, I think of a bimodule is to a quantum channel what a Hilbert space is to a state. So if you take a state and you look at its sector, like all the little local perturbations you can make of that state, you get a Hilbert space representation of the local observables. Similarly, if you take a quantum channel and you do perturbations of this, you can formally build a bimodule associated to it. So a bimodule is kind of like the sector, a super selection sector of a channel or something like that. And what this DHR thing is the super selection theory of the trivial channel. So if I take the trivial channel and look at its sectors that are kind of localized, the same way you would define sectors of a state that are things that are quasi-equivalent outside of some local region or something, that's what's going on here. You're kind of taking because there's no states around, right? No states, no Hilbert spaces. Everything's happening at the algebraic level, but this still works because you're doing a super selection theory of an identity quantum channel. There's always an identity quantum channel. So that's kind of philosophically what's going on. Okay, anyway, and then, so proving this theorem is hard. Proving this theorem is not hard. Okay, this just follows kind of formally from the definition, but for it to be useful, like I said, you need to know what the DHR thing is, and this is pretty technical. But anyway, okay, so that's that, and so if alpha is KW, bounded spread iso, then DHR alpha is EM swap. Okay. All right, good. So so what do I have to say about that? What can you do with this? So this doesn't give you a complete classification, understanding how this thing acts. It gives you a lot of information, and hopefully it gives you the right information to be complementary to something like a numerical index.
Sorry, is there also a numerical index?
Yeah, there is also a numerical index that uses subfactor theory that I didn't write down. That is a complete index in the case of a fib chain where there's no braided auto equivalences of the center, like this invariant is trivial.
This is like additional torsion invariance?
Something like that, yeah, it's like an additional torsion invariant, that's right. Yeah, that's how you should think about it. And it's kind of topological in nature. I mean, they're all topological invariants, so I mean, but like it's valued in like a TQFT thing instead of being valued in a number. Yes.
Is it actually independent of this other invariant, or is there a relationship?
No, they're not independent. They're not independent, and I don't know the exact relationship, but they're definitely not independent. So determining what the DHR, what this automorphism is, greatly restricts what values you can have on the index. But I don't know if it like all those restrictions are realized or not. I think it depends on the specifics of the spin chain, but which object X you pick. Yes.
So could you just like give the number for fib, like?
Yeah, so it's just, so just regular translations.
Yeah.
It's just that. But the index values are tau to the n, where this is the golden ratio. But the index of tau is just the index of a translation. So up to finite depth circuits is just translations. There are no generalized translations. It's like honest translations are all you have. And the index values are the golden ratio. But of course, maybe you want to take, instead of the index, maybe this suggests you should take log of the thing, and then you see this group is just isomorphic to Z. So QCA modulo finite depth circuits on just the fib spin chain is just isomorphic to Z, just translation. So it's kind of boring. But you don't expect this to work. This index could never, so the reason that or what I want to say is that one of the things you learn from this is you can show that the group of QCA modulo finite depth circuits is not abelian. And this is interesting because in the non-symmetric case, so for real spin systems, in every dimension, you can prove this group is an abelian group. But in the symmetric case, it's not abelian. Okay, and you can use this index to kind of see it. You can just build some QCA and look at their DHR index and see that up to finite depth circuits, they can't be abelian. Because it surjects onto a non-abelian subgroup of braided autoequivalences. Okay, good. All right, so that's the first thing. But let me tell you this other thing that you can do, which addresses the second question to some degree. And so I'll go pretty quick. But the second question was, suppose that I have my fusion spin chains sitting inside PAP and ADY sitting inside QBQ. And I have a bounded spread iso alpha from ACX to ADY. And I want to know when I can extend this to a bounded spread isomorphism between PAP and QBQ. Well, the first thing to note is that associated to this is a Lagrangian algebra in the center of C. Okay? Lagrangians, I'll say L in Z of C and K in Z of D, respectively. So this kind of inclusion, the spatial realization of the spin chain, is captured by a Lagrangian algebra. And okay, this was kind of the definition of what this was, that we define as using, if you use these categorical symmetries, if you use the actual definition coming from like a weak-Hopf algebra or something like that, then this kind of comes, there's an associated module category, and so you get this Lagrangian algebra, essentially from the definition here. I'm not claiming that every abstract inclusion of every abstract spin chain into something that looks roughly like this has this form, although something like that's probably true, but I don't have a theorem of that form yet. But in practice, all these fusion spin chains, like when you realize them as like operators on an anion chain or as symmetric operators under categorical symmetry, they all come with a Lagrangian algebra associated. So the theorem is the following: a bounded spread isomorphism between these spin chains extends to a bounded spread isomorphism between these if and only if the associated autoequivalence of the DHR categories takes this algebra to that algebra as algebras. And in fact, you can say something more specific. Liftings from here to here are explicitly parameterized by algebra isomorphism. So let's see, I'm basically out of time. I have enough time to write that. So this is actually a paper that is not, what I'm about to say is should appear on the archive this week sometime. And this is with one of my students, Anna Chats and Dominic Williamson. Following. So alpha extends, or extensions of alpha to a bounded spread iso alpha tilde from these kind of fake real spin systems are parameterized by algebra isomorphisms. Between what? Well, you take DHR of alpha, this gives you a map between the Drinfeld centers, so you can plug in L, and this pops you over into the Drinfeld center of D, and so I can ask this to be isomorphic to K. And each choice of algebra isomorphism that does this gives me an extension. So I'm not talking about up to equivalence, I mean on the nose, just literally bounded spread isomorphisms that happen to restrict to alpha on these subalgebras are parameterized by choices of algebra isomorphisms, and these themselves form a torsor over the automorphism group of this algebra internal to the category. Okay, and so you can kind of answer this question of when the QCA spreads, when the QCA extends. So in other words, this helps you figure out when you have an interesting duality or not, in terms of this associated autoequivalence of the braided tensor category that you construct. Okay, and so that's the that's the theorem. And you can also say something about symmetric QCA, which are like QCA on a real spin system that happen to commute with the symmetry. So this is, kind of like working backwards. You start with the QCA that's defined only on the symmetric observables, then you extend it up to the whole spin system, and then you ask, when does that extension actually commute with the symmetry? And so you can answer that question too, in terms of this, and you recover other results in the literature about the H2 index for symmetric QCA. So. Okay, so anyway, that's all, and I will stop there. Thank you.
Questions?
Can you give an example of where you get an extension? Obviously, Kramer's-Ronne it doesn't extend, right?
Yeah, that's right.
What's one that does?
Yeah, it's good. So here's one that does. So take any old fusion spin chain, ACX, so for any fusion category, NEX, and take any autoequivalence of that fusion category. That defines a spread zero autoequivalence of the fusion spin chain. And in general, it's not a circuit. It depends on you if you look at how it acts on the Drinfeld center, but in general, those won't be circuits. Those will all extend to the kind of standard anion chain. If that makes sense. Another thing you can do is you can look at, so if you have like this group representation thing and you have a non-abelian group G acting, then any outer automorphism of G will extend to a spatial realization, even though it doesn't actually commute with the symmetry. So if you take an outer automorphism of G, that kind of gives you a, yes, that's my claim. That's just a special case of the thing I said before, because outer automorphisms give you monoidal equivalences of rep G by kind of permuting the action and then applying it. And that gives you an autoequivalence of the fusion spin chain, but it actually extends to the whole concrete spin chain. You can just represent it by unitaries. So in my paper where I do this, I give a bunch of examples of that form. So in my paper about DHR bimodules, the main examples I consider actually of that form, where they're just group actions, and they do extend to the whole spin chain. But interestingly, they extend to the spin chain and don't commute with the symmetry, which is kind of an interesting phenomenon. But they do preserve the subalgebra of symmetric operators and therefore define symmetric QCA as well. Yes.
So if I have something that is width trivial, does that tell me something about like the size of the group or?
If you have something that's width trivial,
Yeah.
so like a modular tensor category. Well, so I'm not sure, because these fusion categories, this whole story, these are fusion categories, they don't seem to care about braidings. So in this dimension, I'm not sure, but in 3 dimensions, that's where, the conjecture is that there's at least a surjective homomorphism from the group of QCA in 3 dimensions to the Witt group of modular categories. And that's an interesting question, but it's kind of orthogonal to this, because those are real spin systems. They're not talking about these kind of symmetric duality things.
In this discussion for Kramer's-Ronne,
Yeah.
is there some way to rephrase it or in some way in terms of the Tambara Yamagami?
Yes, yeah, indeed. So that's exactly what's going on here. Good. So, and that's how you can get lots and lots of examples that do generalize this. But you can think of, so take the fusion spin chain for Tambara Yamagami with generated by the object rho. Okay, well, this fusion, if I take rho squared, this is secretly that object, right? In vec Z2. So what I can do is I take my spin chain for Tambara Yamagami and I coarse grain it so that a single string is vec Z2. But nevertheless, I can still do a shift by one string. Because that pops me, even though just shifting by one string pops me locally out of vec Z2 and into Tambara Yamagami, since I have an infinite thermodynamic limit, I'm actually in the same spin chain. And that's exactly what Kramers-Wanier is doing. So this is kind of a representation after coarse graining of that one. And you get what you get from this picture with this kind of secret factorization into rho tensor rho, right? You get from the secret factorization ability to shift by one, which you don't see if you just work in this category. Or you can see it, but you have to work hard to come up with a Kramers-Wanier duality. But here, it's just supernatural. Once you know Tambara Yamagami's there, you just see, oh, it's shift by one. And then you can generalize this for any G-graded extension of a fusion category. You can play the same game where you take some generator in the G-graded component, take tensor powers of it, so it's a generator for the even component, and then shift by one. And that will implement basically any autoequivalence of the center you want to. And so that's how you can see that you can get enough of these autoequivalents of the center around. They're not just like rare things. They're not restricted in what values they can take. But yes, indeed, Kramers-Wanier duality is somehow really about this Tambara Yamagami category in some sense, which is basically what we were talking about earlier. Yes.
So which parts of the story don't carry over to higher dimensions? So for example, if I think about like the 2D Ising model, this DHR thing.
Yeah, good. So the DHR thing makes sense. The problem is the DHR thing is not the right thing in higher dimensions. What you really should be getting is a braided fusion 2 category for a 2D abstract spin chain. And so the fusion category level is supposed to go up. So you do get a DHR category, but it's symmetric in higher dimensions. And so you're just getting this small piece of this big braided fusion 2 category. And so the story carries over, you're just getting less information than you are in 1D because you're missing this whole braided fusion 2 category. So there should be a DHR braided fusion 2 category. It's just very hard to write down to prove. I mean, I can even tell you what the line defects and stuff are supposed to be. It's just very hard to prove something's a braided fusion 2 category, but that is an ongoing project. And in general, you should have a braided fusion N category. I mean, what's going on here is another way to think about these fusion spin chains is living at the boundary of a higher dimensional topological order. And it's that topological order of one dimension higher that this DHR category is capturing internally to the spin chain. So in some sense, you can think about this spin chain as being kind of like a holographic dual of the bulk topological order, and this DHR category is telling you this holographic dual remembers the topological order of the bulk. And that story should be true in any dimension. It's just much harder to make that precise mathematically and prove. I see.
So this fact about braided tensor category, I guess that's true, but you're saying it's only.
It's just gonna be symmetric. It's gonna be rep G, or like in 3D, if it's a digraph Witten theory, you're just gonna see rep G and you're gonna miss all the interesting line defects and stuff. And that information should be there. And the bounded spread isomorphism, like classifying, it should depend on how it acts on all that complicated information. But this DHR category is just seeing a tiny little piece. Yeah.
Does the bounded spread isomorphism kind of only makes physical sense when you have a thermodynamic limit? Because you need some bound that's sort of much smaller than the size of the system, right?
So it is certainly only makes sense as a isomorphism in the thermodynamic limit. So you can define it locally, right? Because but it's not going to be a unitary locally. Locally, it's going to be, I'm going to send this algebra into this algebra somehow, and it's not going to be a unitary. You only see that it's an isomorphism, or that it's implemented by a unitary or something in the thermodynamic limit. So you can still make, and actually this was one of the problems in the early days of quantum cellular automata. People were struggling to find the right definition because they weren't thinking they had to go to the thermodynamic limit to formally define it. But yeah, it is certainly the easiest to define as an isomorphism in the thermodynamic limit. But you can kind of locally make sense of it. It's just the isomorphism property you only see.
Any further questions? So if there's no further question, let's thank the speaker.